Alright, let's start the second lecture on Chapter 2. We will introduce a new set of machinery that will allow us to reduce a further wider range of optimization algorithms as fixed-point iterations with averaged non-expansive operators. The first such tool is the resolvent. The resolvent of an operator A is defined as this inverse. So given the operator A, we add the identity operator, and then we take the inverse, and we write that as J of A. The reflective resolvent of the operator A is written as RA, and is defined as 2 times JA minus the identity operator. The reflective resolvent is also called the Cayley operator or the reflection operator. Oftentimes, we will scale the operator A by a positive constant alpha, and then take the resolvent, and then consider the resolvent or its reflected resolvent, and in which case we will write J of alpha A and R sub alpha A. If the operator A is maximal monotone, then the reflected resolvent is non-expansive and also single-valued with full domain. So the domain of the reflected resolvent is all of Rn. And if A is maximal monotone, then the resolvent is 1/2 averaged with full domain. Let's first prove non-expansiveness of the reflected resolvent, and thereby we will be proving the averageness of the resolvent. Let's assume that x, u, and y, j are input and output pairs of the resolvent. Well, if x is the input to the resolvent of A and u is the output, well, remember that means that u is in the I plus A inverse x. So this is equivalent to u plus a u contains x, and that's what we have here. The same kind of reasoning applies to the pair y, j, so we write that over here. Then, since x minus u is in the output of the operator A, evaluated at u, and since y minus v is in the output of A, evaluated at v, by monotonicity of the operator A, we have this inequality. X minus u minus y minus v, those are the outputs of the operators, operator A at point A and v, and then u minus v, those are the inputs. So we have this monotonicity relationship. Remember, the reflective resolvent is defined as 2j minus identity. So this implies that x, u, being an input-output pair of the resolvent of A, implies that x, 2u minus x is an input-output pair of the reflective resolvent of A. So we take 2u minus x and 2v minus y, and we subtract them and take the norm. And then we just expand out these terms. So we get x minus y squared, that's what comes from here. And then we expand the cross terms, and then we expand the 2u minus 2v term and write things out, and we get this expression. And this, and because we've established that this is non-expansive, it's non-negative by this previous inequality. So the right-hand side is less than or equal to x minus y squared. So this establishes that the reflective resolvent is a non-expansive operator. And since the resolvent of A can be conversely defined as the 1/2 averaging between the reflective resolvent and the identity operator, this shows that the resolvent is 1/2 averaged. Now, 2 slides ago, we claimed that the reflected resolvent is non-expansive and that the resolvent is 1/2 averaged, and we just showed that. Also, the non-expansiveness directly implies the single-valuedness of these operators. But furthermore, we also claimed that both the reflective resolvent and the resolvent has full domain. Well, this fact, the full domain property of the resolvent, follows by the Minty surjectivity theorem. The Minty surjectivity theorem states that the domain of the resolvent with respect to A is all of Rn when A is maximal monotone. Now, if you go back and think about how we proved the previous non-expansiveness conditions, we used the fact that A was monotone, but we have not yet used maximality of the operator A. Well, the maximality of the operator A is important in its application of the Minty surjectivity theorem. This is a desirable conclusion, which we will discuss again soon. But in order to establish this full domain condition, we need to utilize the maximality of the operator, and that because that is required by the Minty surjectivity theorem. When the underlying dimension n is equal to 1, so when the underlying dimension is 1D, the result, the Minty surjectivity theorem, is somewhat intuitively easy to see, and it is not too difficult to prove. However, when the dimension is higher, in general, when the dimension n is not equal to 1, then the Minty surjectivity theorem is a highly non-trivial result. So in today's lecture, we will simply state the fact that the Minty surjectivity theorem implies the full domain condition, and we will prove the Minty surjectivity later in chapter 10. Here's an interesting fact. The zero set of a maximal monotone operator is a closed convex set. It could be empty, it could be all of Rn, but in any case, it's a closed convex set. Remember, an empty set is also considered a closed convex set. Let's prove this result. So the zero set of the operator A is equal to the set of fixed points of the resolvent. Why is that so? Well, 0 is in the output of Ax if and only if we add both sides to this inclusion. So x is in the output of x plus Ax. And then, well, this is just identity plus the operator A applied to the point x. So we take the operator, move it over, and write it as the inverse, and then we get the resolvent with respect to A applied to x is equal to x. Note that because we have established that the resolvent is a single-valued operator, we can now use the equality symbol rather than the inclusion symbol. Since the operator resolvent is a non-expansive operator, the set of fixed points of the resolvent with respect to A, which is equivalent to the zero set, is a closed convex set. Now at this point, you may question, where was the assumption of maximality used in this proof? Well, the proof relies on maximality through this condition. So more specifically, previously we established that if JA, which maps from Rn to Rn, is non-expansive, then fixed point of JA is closed convex. We showed this result, but in this analysis, we had this full domain condition. This full domain condition is ensured by the fact that the domain of the resolvent is equal to all of Rn by the Minty surjectivity theorem. Okay, then let's take a look at a few examples of monotone operators and their corresponding resolvents. Let A be a monotone linear operator that is represented by a symmetric matrix. Then a monotonicity of A implies that A has eigenvalues in the interval 0 to infinity. By the way, A is assumed to be represented by a symmetric matrix, and the eigenvalues of a symmetric matrix are real. So the monotonicity ensures that the eigenvalues lie between the interval is bigger than or equal to 0. And then the resolvent, which is represented by the matrix identity plus A inverted, has eigenvalues in 0 and 1, with 0 not included. Then the reflective resolvent, which is defined to be 2JA minus I, can also be written in this case as identity minus A composed with identity plus A inverse, or identity plus A inverse composed with identity minus A. This is referred to as the Cayley transform of the matrix A, and it has eigenvalues between -1 and 1, with -1 excluded and +1 included. Here's another example. So let's identify a complex number Z, a scalar complex number Z, with the linear operator from C to C defined by multiplication. So given a complex number x as input, the linear operator is Z times x. And the action of the linear operator Z is Z times x, where Z times x is complex multiplication. Here the idea is that we are identifying the space of complex numbers, the complex plane, as with the two-dimensional space R2. If we equip the space of complex numbers with the inner product x comma y. This is just the usual element-wise inner product, but it can also be written as the real part of x times y complex conjugate. This multiplies the real part and adds that to the product of the imaginary parts. Then the complex number z is monotone if and only if it is within the closed right half plane. If we were to visualize it, z is monotone if and only if it resides in this region where this point is the origin. The resolvent 1 plus z inverse for a monotone operator z lies within this disk. So the disk has center 1/2 and has radius 1/2, but the origin is excluded. So points lying within this region, those are the resolvents of a monotone complex number. Next, we have the resolvent of a subdifferential. Let f be a CCP function and let alpha be a positive scaling parameter. Then the resolvent with respect to alpha times the subdifferential of f is equal to the proximal operator with respect to alpha times f. This identity is what connects the notion of the resolvent with the proximal operator. Let's prove this. So first we have, this inverse is j alpha partial f. So first we consider an input-output pair x comma z with respect to the resolvent. Well, on the right-hand side, we have an inverse operator, so we put that on the left-hand side, and we get a z plus alpha partial f z contains x. Now we can reorganize this, so this is equivalent to 0 contains in alpha partial f z plus z minus x. And then what we have here on the right-hand side is the optimality condition of minimizing this convex function. So we put a partial z here and write it in as such. We can write this as an argument. And then this argument defines the proximal operator with respect to alpha f. Next, we have the resolvent of the subdifferential of a conjugate. We define the convex function g as f star composed with a transpose, where f star is the conjugate function of f. We assume f is a CCP function, and we furthermore assume this regularity condition. This regularity condition ensures that the function g is a CCP function, and it also ensures that the chain rule that we will apply soon is valid. Under these conditions, the proximal operator with respect to alpha g can be evaluated by solving this particular minimization problem and then computing the matrix vector product A times x and then subtracting it from u. Let's prove this. So let's assume v is an output of the proximal operator with respect to g, where u is the input. Well, this is the proximal operator, and it's written as an inverse. So we take the inverse and apply it to the left-hand side. So that's so then we have I plus alpha, or we have a v plus alpha partial g applied to v contains u. But partial g is equal to a partial f star a transpose by this regularity condition. So we apply the chain rule to convert partial g into this. So then we have v plus alpha a partial f star a transpose v contains u. Then this is partial f star, that's a set valued mapping, that's a set valued operator. And this inclusion, what this inclusion means is that there is an output value of the set of partial f star, which we name x, such that x is within this output value, and then we have this holding with equality. Then we reorganize this expression, so we take the alpha ax and put it on the right-hand side, and we are free to do that because alpha times ax is now it's not set valued, it's just a single valued vector. And then here we have partial f star. Well, f star, because f is CCP, partial f star is the inverse of partial f, so we apply this to the left-hand side and then use the formula that partial f star is the inverse of partial f. And then here we have v, so we substitute the value of v, which is written over here, to get this expression. And finally, we recognize that if we take this term and put it on the left, well, this expression is equivalent to the optimality condition of this optimization problem. So we can now write V is U minus alpha AX, where X is obtained by this minimization. So to repeat, this result tells us that if we wish to evaluate the proximal operator with respect to G, where G is defined as F star composed with A transpose, then we can solve this minimization problem and perform this linear algebraic calculations. The projection onto a set is a computational primitive used widely in applied mathematics. The resolvent generalizes the notion of the projection. So if C is a non-empty closed convex set, then the resolvent with respect to the normal cone of C, which is the proximal operator with respect to the indicator function of C, is equal to the projection onto the set C. So in this sense, the resolvent generalizes the projection operator. Next, let's evaluate the resolvent of the KKT operator for linearly constrained problems. Let's consider this Lagrangian, f of x plus u inner product ax minus b, because this Lagrangian generates this linearly constrained convex minimization problem as its primal problem. Let's compute the resolvent with respect to the saddle subdifferential of L. Let me first state the result. The resolvent of the saddle subdifferential applied to x comma u can be evaluated by first computing this minimization problem to obtain the value y, and then computing this linear algebraic computations. Here, L sub alpha is the augmented Lagrangian, where we have this first term, which is equal to L of x comma u, and that is the Lagrangian. So this is the Lagrangian. But in addition to the Lagrangian, we have this term, this quadratic term, and together we refer to this as the augmented Lagrangian. Okay, let's prove this result. So remember, L of x comma u is f of x plus u inner product with ax minus b, and partial L is equal to partial xl and partial u of minus L concatenated. So this is equal to partial f plus a transpose u x, and then this is equal to minus a x. And we can write this as partial f 0 plus plus 0, 0, a transpose minus a, x, u. So we can now express the resolvent of the saddle subdifferential of L applied to x comma u and y comma v being the output of the resolvent evaluation in this way. So we take the left-hand side, which is the inverse of the identity plus alpha partial L, applied to the right-hand side. So x comma u is y comma v. So this is the identity operator part. And then we apply the saddle subdifferential scaled by alpha to y comma v to get this. Now we reorganize some terms. So we take the alpha times partial f to put it over here. We take alpha times the constant vector b and put it over here. And then yv and then a transpose v minus a transpose y. We put that all here as a matrix vector product. Next, what we do is we multiply this linear system of inclusions by this left invertible matrix. So this matrix is an invertible matrix, so that means multiplying by this matrix results in an equivalent system of inclusions. When we left multiply by this matrix to the left-hand side, we get this thing. When we multiply this to here, we get this thing. And now the important part is that when we multiply this to this matrix, we get this lower triangular matrix. Now this first line is now independent of V. So if you notice, that in this system of inclusions, well, x and u are provided inputs to the resolvent evaluation. So x and u are just determined values. Here, v is multiplied to 0, so there's no dependency on v here. And so the only unknown in this first line of inclusion is the y. So we can first compute the quantity y, and then once the quantity of y has been computed, then we can move on to the second line to utilize u, which is known, y, which is known, and then we can compute the value of v. This technique is referred to as the Gaussian elimination technique, and we will spend more time with this technique and explain it further, explore it further in detail in chapter 3.4. So therefore, in the first line of inclusion, there is no dependency on v, so we can reorganize it to get this inclusion, which depends on y and x and u, but does not depend on v. And then here we have the second line of inclusion, which defines v. The first line of inclusion is equivalent to this optimality condition, so we can write it, obtain the value of y by solving this minimization problem. And once the value of y has been obtained, we can plug it in back into here to obtain the value of v. Next, we quickly state some useful resolvent identities. So let A be a maximal monotone operator and let alpha be a positive scaling factor. Then the operator B, defined as ax plus t, where t is added to the output of the operator A, well, B is also a maximal monotone operator, and the resolvent with respect to B can be evaluated with this formula. If we define the operator B with a of x minus t, where t is now subtracted out from the input rather than the output of the operator A, then the resolvent with respect to B can be evaluated using this formula. And then if B is the negation of the operator A, but the input is also negated, so the operator A is negated, but because the input is also negated, and with a shifting t, the operator B is still monotone, and it is also maximal monotone. So the resolvent with respect to B can be evaluated using this formula. These identities are relatively straightforward to prove, so I'll leave that as an exercise, but these identities will come up from time to time, so it's useful to formally state them here in writing. Next, we have the very elegant inverse resolvent identity. So the inverse resolvent identity has this form. So the resolvent of A multiplied by alpha inverse and we add that to alpha inverse times the resolvent of A times A inverse, alpha times A inverse, with the input scaled by x is equal to x. And this holds for any maximal monotone operator A, any input x, and any positive scaling alpha. Now this formula is perhaps not the most elegant thing, but in the special case where alpha is equal to 1, then we get this extremely elegant formula. JA plus JA inverse is equal to the identity. The special case of the inverse resolvent identity for the proximal operator with respect to f is written in this way. So it's exactly the same formula, but just with the resolvents replaced with the proxies. And this identity is also referred to as the Moreau identity. The consequence of these identities, the inverse resolvent identity and the Moreau identity, is that the proximal operator with respect to f and the proximal operator with respect to f star, they require the same computational cost. If I know how to compute this quantity, then I essentially know how to compute this quantity, and vice versa. The same holds for resolvents. So if I know how to compute the resolvent with respect to A, then I essentially know how to compute the resolvent with respect to A inverse. Next, let's briefly step away from the lecture content and instead solve an exercise problem. Specifically, let's together solve exercise 2.1 from the book. The problem is entitled, When T inverse is a left inverse of T. The problem statement is to show that if x is within the domain of an operator T, and if the operator T inverse is a single valued operator, then T inverse composed with Tx is equal to x. In other words, T inverse serves as a left inverse of the operator T for inputs x that reside within the domain of the operator T. Let's prove this together. So since x is within the domain of the operator T, there exists an output y within the evaluation Tx. So in other words, the Tx is not an empty set. Since y is in tx, by definition of the inverse of an operator, x is in t inverse y, and by definition of the composition of operators, we have x is in t inverse tx. So the way we understand this is that we put in parentheses here, and tx is a set that contains y, and then the output of t inverse evaluated at y contains x, so x is indeed contained here. Next, we let x tilde be perhaps another output of the operator t inverse evaluated at tx. Well, this would be, by definition of the operator inverse, this is equivalent to saying that there exists a y such that x tilde is equal to t inverse y. Well, remember, we're assuming that t inverse is a single valued operator, so we're writing using the equality notation here. So x tilde is equal to t inverse y, and then y is an output of the operator t evaluated at x. Then, well, this is equivalent to there existing a y such that this part remains the same, but we take this t and then put it over here, so we write t inverse applied to y is equal to x. But t inverse is a single valued operator, so when we provide in a single input y, the output ought to be the same, so that tells us that x tilde is equal to x. So in summary, we showed that x is an output of the evaluation t inverse tx. And by the way, to clarify, here we're using the set notation because at this point, we are not yet sure whether the right-hand side is a singleton set, because although t inverse is a single valued operator, tx is potentially multi-valued. So the right-hand side is a single valued operator acting on a set. So the output may not necessarily be a singleton. But in the first step, we show that x is within the set, and in the second step, that we show that x is the unique, is the only output, is the only element of the set, and therefore we can replace this inclusion with equality. Next, we have the reflected resolvent identities. So the first identity states that if A is maximal monotone and furthermore single-valued, then the reflected resolvent can be written in this way. Identity minus alpha A composed with the resolvent of A. Let's prove this. So first, the reflected resolvent of A is by definition 2 times the resolvent of A minus the identity operator. Next, we can write the identity operator as I plus alpha A composed with I plus alpha A inverse because the operator A, this operator, is single-valued. This fact, where we replace identity with this, formally follows as a consequence of exercise 2.1 of the book. Finally, continuing on from this step, here we interpret the 2 as 2 times identity composed with this operator. So we pull out the resolvent to the right, and then we have 2 times identity minus identity plus alpha A, and we get this. The next reflected resolvent identity is for the general case where the operator A is maximal monotone, but not necessarily single-valued. Remember, in the previous identity required that the operator A be single-valued, and in particular, it was the assumption of single-valuedness was utilized in the step where we referred to exercise 2.1. In the general case, we can write the reflected resolvent composed with I plus alpha A as I minus alpha A. Let's prove this. So the operator A is, in general, a multi-valued maximal monotone operator. So it may or may not have full domain. If the operator A does not have full domain, then we do need to exercise care and consider the 2 cases where an input x belongs to the domain of A and the input x does not belong to the domain of A. For the first case, let's consider the case where x is in the domain of A. Then the reflected resolvent of A composed with I plus alpha A evaluated at x is by definition equal to this, because we first evaluate I plus alpha A, and then compose that with 2JA minus identity. Then we have I plus alpha A inverse composed with I plus alpha A canceling out to become the identity operator, again by formally appealing to the exercise 2.1 of the book. This term is just written over here. So now we have 2I x minus identity plus alpha a applied to x. So we evaluate things out, and we get I minus alpha a. Okay, so this establishes the equality of the left-hand side and the right-hand side for inputs x that belong to the domain of A. Now, if the input x does not belong to the domain of A, well, both the right-hand side and the left-hand side evaluates to be the empty set. And the empty set is indeed equal to the empty set, and both sides therefore become equal.